feel lucky to introduce Marissa Dudek for her master's defense presentation on behalf of the committee, which consists of myself, Ryan Mills, Tamlin Pavelski, and then Shane McGarry at James Madison University. And Marissa comes here from the time at James Madison, and then an internship with JPL and the Space Museum. Yeah, okay. All right. And other great things. Marissa's done a great job at her time here during this chaotic time of ours. And I'm excited about letting her share with you what she's been working on, driving herself with this, the committee, the three of us, helping where we can. So without further ado, Marissa.
Thank you, Ryan. Well, hello. Again, my name is Marissa Dudek. Thank you for coming to my thesis seminar, where we're going to be talking about what I did here the past couple of years. And I actually started this presentation at my time at JMU in 2017. So I've been working on this for a little while, so we got a lot to talk about, but it's awesome because we're talking about craters. So what we're talking about here is the work that I've been doing on building the atmospheric effects model, AEM or AIM for short, and how we've been using it to estimate projectile survivability for crater formation on Venus, Earth, and Mars. And the main question that this thesis is asking is which projectile characteristics, i.e. the mass, velocity, and angle of trajectory, are most likely to survive atmospheric passage to form a crater on Venus, Earth, or Mars. And we ask this because impact craters are one of the most prevalent geologic features in the solar system. They're found on nearly every terrestrial planet, satellite, asteroid, and meteoroid. And we can use the size and frequency of these craters to tell us a bit about the surface's age and evolution. So for instance, if we look at the moon, which has countless craters, anywhere from a couple of millimeters in diameter up to over 1,000 kilometers in diameter, and we look at the topography, we see that we have a dichotomy in the crater distribution. So the highlands shown here in red and orange are very heavily cratered with large overlapping craters, while the lowlands are less cratered, where they're smaller and far and few between. And thanks to samples that we've collected from the Apollo missions and from more recent lunar landers and satellite missions, we've been able to determine that the ages of these highlands that are heavily cratered are significantly older, more than 4 billion years, than the lowlands, which are closer to 2 to 3 billion years. And that even some of the most recent craters that have been formed on the moon, Copernicus and Tycho, are less than 1 billion years old. So from this, we can see that the moon has recorded more than 4 billion years of crater formation. And with this, we can reconstruct a crater chronology, the timing of cratering, where the formation of craters was significantly higher more than 4 billion years ago as the solar system was forming. And there were these huge rocks that were just flying around in space, hitting each other. And over time, as the planets grew larger and larger, they eventually cleared their planetary orbits, and the flux of material that was flying around in space got smaller and less frequent. And so too did the crater formation. So the moon records this crater chronology, and we can take this now to other planets. So if we look at Mars and its topography, we see that it has a similar dichotomy in crater distribution, where the older highlands are more significantly cratered than the younger lowlands. And it's been recently hypothesized that Mars could have had a liquid ocean in its northern hemisphere that's erased all of the craters, or the majority of the craters that we would have seen. And so with this, we can see that the craters can not only tell us about the age, but also the environment that could have been there at the time, and how it's changed over time. And if we take this over to Earth and our topography, we see similar highlands and lowlands, and we also see a similar dichotomy in crater distribution, where we have the majority of craters clustered on the older highlands rather than the younger oceanic crust. Now, this is because our planet is constantly recycling its oceanic crust and has thus destroyed the craters that we would have seen there. Now, Earth also has significant weathering and erosion processes that is destroying some of the craters that we would see on the surface. And we see craters that are generally a couple hundred kilometers in diameter at their largest, down to a few hundred meters in diameter at their smallest. And so if we take this now over to Venus and its topography, we see that it has a similar highlands and lowlands, but we don't see the dichotomy in crater distribution. The craters shown here in this kind of green dots are actually pretty randomly distributed across the entire planet. There's no highlands versus lowlands correspondence. And so with this, we have come to think that Venus has possibly gone under one or multiple regional or global resurfacing events where the entire crust has actually been recycled and has reset the crater population. And if we look at the craters on Venus, we can see that they range anywhere from a couple of hundred kilometers in diameter, like we see on Earth, but they really only go down to about 1.5 kilometers at their bare minimum. And we don't see any below 1 kilometer. And the ones that we do see that are within this 10 to 1 kilometer range are very irregularly shaped. They're overlapping, they're not circular. And so this tells us that the atmosphere has probably broken the projectile before it came through, and it's splattered in multiple pieces on the surface. So we can see that Venus most likely has significant atmospheric effects that are affecting the crater distribution that we see. So we need to take these atmospheric effects into consideration when we're trying to compare the lunar chronology to these other planets. We see that the moon doesn't have an atmosphere, so the initial characteristics of the projectile are relatively unchanged to when it hits the planet. On Mars, which has a slightly denser atmosphere, they're going to be slowed down just a little bit more. They're going to heat up and ablate or lose mass over time. On Earth, which is a little bit more, they're going to not only slow down and lose mass, but they're also going to fragment into more pieces. And we don't quite know what's going on Venus. We know that it probably has a very high rate of atmospheric filtering, but we're not quite sure the altitudes of where that's happening. So we want to be able to look at that. And that takes us back to our research question of trying to figure out what projectile characteristics can actually get through to form a crater on these different planets. So the first thing we wanted to do is we wanted to be able to build a model that can simulate these atmospheric effects on the different planets. So what we did was we built a mechanical model in MATLAB that takes a projectile population with a given mass, velocity, and angle of trajectory and throws them through the atmospheres of Venus, Earth, and Mars and directly to the lunar surface. The atmospheres of these different planets are modeled with temperature, pressure, and density profiles at altitude. Now, there's a lot of numbers on this slide, but what I want to get across is that density is the leading contributor to what is being filtered here, right? If the atmosphere is more dense, it's harder to get through. And we see that a density of 0.01 kilograms per cubic meter is at an altitude of about 80 kilometers for Venus and 20 kilometers for Earth. So we can kind of start to see how this is going to affect these projectiles as they come through. Now, as those projectiles are going through the atmosphere, the model is tracking the change in the characteristics at each time step. In our case, that's every 10th of a second. It's tracking how the mass and velocity and altitude are changing between steps. And it's recording that at each time. And if the projectile can survive to hit the surface, as in it has a mass greater than 0 and a velocity higher than the terminal velocity, it will strike the surface and the final projectile characteristics are pulled to then create a crater, where the diameter and the depth are then measured. So going into a little bit more technical here, the model takes into account various target characteristics and atmospheric conditions into account when it's trying to represent these atmospheres. And by representing the atmospheric effects, we're doing the change in velocity, angle, and ablation over time, and trying to figure out what type of crater is formed afterwards. Now, as we were going through the literature, we found not only one equation to calculate each of these different differential equations, but we found quite a number of equations of how to calculate these. So the model not only takes into account one equation, but you can actually change which equation and which methodology you want to use to calculate these different parameters. So we have 9 different velocity equations, 4 different angle equations, and 6 different ablation equations. Now, these equations range from like 1971 all the way up to like 2016. So we have a wide array of methodologies that are in the model and ready for people to use if they want to mix around the methodologies to try and figure out what's going on with the projectiles. Now, these are relatively simple to model, but fragmentation, dispersion, and disintegration is pretty hard. And if we look at this video of the Chelyabinsk meteor sighting over Russia in 2013, we can see that it's a pretty catastrophic nonlinear process where the projectile is coming through, heating up, fragmenting, will eventually burst, and then disintegrate in the atmosphere. So we're trying to model this. And how we've done it is we take the projectile, a single spherical projectile coming through the atmosphere, and when the pressure on the leading edge exceeds the yield strength of the meteor itself, it'll break into one additional piece that's half the mass of the next largest piece. And it does this at every time step that that pressure is exceeded. And those fragments will ablate over time and will also disperse laterally from each other in a process known as pancaking, because they disperse like a pancake. And we can see that with this Chelyabinsk example, the projectile comes in, starts to pancake as it's fragmenting. It eventually reaches a critical mass and bursts, and then the remaining pieces are left to kind of just burn up in the atmosphere. And a projectile bursts when the pancake factor, the difference or the ratio of the projectile's diameter to the original diameter is exceeded. Then it'll blow up and it'll start to burn up in the atmosphere. So we're trying to model these very complex processes in a relatively simple manner. So now that we have a model that takes into account all these different effects and can throw them through all these different atmospheres, we want to be able to see how sensitive it is to different equations and assumptions that we want to use. So we first wanted to test the equations. Now these are some of the equations from Baldwin and Schaefer in 1971 on how the velocity, mass, and angle change over time. What we found is that velocity has the highest sensitivity, or the model is most sensitive to changes in the velocity equation, given that the velocity is so inherently linked in how much the mass and angle are changing over time. And so if we look at the equations that we tested here, these 9 different ones, they relatively line up in similar impact characteristics from the same projectile with the velocity and the remaining mass. However, one equation was significantly off from the others, and we actually found that this one is meant for meteorites. And so you need to be careful that the equation that you're using is meant for the projectile that you're testing. We also want to look at some of the different assumptions that we're taking into account here, like the heat transfer coefficient, so how quickly heat is moving through the surface, the heat of ablation, the drag coefficient, the shape factor, and the lift coefficient. Now, these can either be calculated or assumed constant throughout the model, and we decided to keep them constant with some of the values that are currently understood with these types of projectiles in the atmosphere and found that the heat transfer coefficient has the highest sensitivity to changes in our model. That's because this constraint is, or this parameter is not as well constrained as some of the others that we have. For instance, lift coefficient, there's not much lift happening on a projectile as it comes hurtling through the atmosphere. But how much heat goes from the atmosphere into that projectile is going to significantly affect how it goes, how it evolves as it goes through. And so here we saw that we tried a heat transfer coefficient from 0.01 up to 0.6, and that significantly affected how the mass was changing. So again, we chose some equations and assumptions that were relatively within the realm of correct parameter space that we had for our understanding of projectile evolution, and used that in our model moving forward. But you can use these sensitivity testing to try and constrain the analytical error of our mechanical models. So now that we had a model and we knew how sensitive it was, and we got it to align to our current understanding, we wanted to actually see if it worked. So we took 4 known terrestrial observations and ran them through the model to try and see if it actually aligns with what we see here on Earth. So the first one that we tried was the Chixculub crater in Mexico. Now, it's about 180 kilometers in diameter. This is an artist's rendition of how it might have looked soon after its formation. We can no longer see the rim, but we can see features from the impact, such as sinkholes and gravitational anomalies, as well as meteorites that were scattered around it that have been able to constrain what the projectile might have been that formed the Chixculub crater. So it's approximately 14 kilometers in diameter, traveling at a 45-degree angle at 17 kilometers per second, with a relatively low density when it comes to meteorites. And what we found was that we threw it through the model, and we got a complex crater that was 135 kilometers in diameter, comparable to the 180 that it is currently. And if we look at the change in velocity and the change in mass, where ablation is the blue solid line and ablation with fragmentation is the orange dashed line, you can't actually see a difference between having ablation and ablation or fragmentation. And that's because these projectile is so large that it's not affected by the atmosphere, right? So that tells us that the model is working correctly for these really big craters, really big projectiles, and it's giving us accurate results. Then we wanted to try and see something for a smaller crater with a smaller projectile. So we looked at Meteor Crater in Arizona, which is about 1.81 kilometers in diameter. And from the different observations of that crater, they thought that it must be about 15 meters in diameter, traveling at the same angle and velocity. 45 degrees and 17 kilometers per second is the average angle and velocity for terrestrial impacts, but it had a much higher density. It was an iron meteorite. You know that from the Canyon Diablo meteorites that we see. And so if we take this much smaller but denser object through the model, we see that it does create a simple crater that is almost exactly the same diameter as the one that we see on the surface. And if we look at the ablation and breakup, the orange dashed line, we can see that the velocity slowed down to about 11 kilometers per second, which agrees with our current understanding. And it lost about 25% of its mass, 50 to 25%. And so this also aligns with what we see with other models. So that's good, right? The model is working for complex craters and simple craters. Now we wanted to try something that's a little bit more unique. So it's the Tunguska meteor that exploded over Russia in 1908. Now, it probably burst at an altitude between 5 to 15 kilometers, and it actually flattened about 2,000 square kilometers of land in this area. And while it was projected to be about the same size as the meteor crater projectile, it's much lower density. So when we run that through the model, we see that it makes a simple crater, even though we don't actually have a crater seen there, And the crater itself is about 410 meters, so relatively small. But we can see that the velocity and the mass are decreasing at a higher rate for this projectile as the meteor projectile, even though it's the same size, but because it's a lower density, it's affected more. So that's good. The model is working properly, even though we have a little bit of a discrepancy, but I'll get back to that in a second. So the AIM underestimates these atmospheric effects for these Tunguska-like events, right? It comes through and it tells us that it makes a crater when we know that it actually didn't. And if we look at the crater that it made, about 410 kilometers, it's very, very tiny to the area that the actual projectile exploded. So it's kind of working, but again, we'll talk about that in a second. So then we wanted to look at the Chelyabinsk meteor, the one that we saw earlier, that flew over Russia in 2013. Now, we have really good observations on this meteor. We have a lot of dash cams, we have a lot of imagery and satellite observations. So we've been able to constrain that this projectile was about 20 meters in diameter, traveling at a much lower angle, about 20 degrees, and was slightly more dense than the other ones, but still relatively less dense. And we saw that the model did burst it at about 12 kilometers altitude, and it didn't form a crater. And so we see that here that the model is correctly modeling complex craters, simple craters, has kind of a hard time figuring out these complex airbursts at lower altitudes, but is able to completely vaporize these ones that we know wouldn't make a crater. Now, if we look at the pancake factor, we remember the dispersion of these fragments. When the pancake factor is exceeded by a factor of 5 here that we've chosen, which is based off of Chelyabinsk et al. 1993, who had a pancake factor between 5 and 10 for Tunguska-like events, we can see that the Tunguska one actually exceeds this 5 projectile limit, pancake limit. And so that tells us that it could have actually burst at an altitude of 11 kilometers and wouldn't have formed a crater. So we're trying to think about how these different projectiles are being modeled through the through AIM. And we can see that for these ones that are more unique, that they actually, we get that they form a crater, but looking at their pancake factor and the pancake limit altitude at which they exceeded that can tell us if they would have actually burst before they hit the surface. So we got all this information, right? We got a model, we tested it, we ran it through Earth, seems good. Now we're gonna run a theoretical population of projectiles through the 3 different atmospheres and see which ones can get through to form a crater. So we created a theoretical population of projectiles with varying densities, diameters, velocities, and angles. So the 4 different densities are iron, stony, and chondritic, our basic meteorite types. Our diameters range anywhere from 1 meter up to 10 kilometers to try and get a range of masses. The velocities are from 1 kilometer to 40 kilometers per second. Again, the average impact velocity for Earth is about 17, so we're kind of getting an average spread around that. And the impact angles range from 15 degrees to 90 degrees relative to horizontal. And we set that 15-degree limit because, as you can see from here, this is a meteor sighting at Grand Teton in 1972, that if a projectile has a really low angle, it might just go straight through the atmosphere and not actually hit the surface at all. So we wanted to limit this possibility because we actually want to be able to make craters. So we set it to about 15 degrees as our limit. So if we look here at the projectiles that went through to Mars and how their velocity and mass remaining evolved over time, we can see here that they didn't really change very much. The width of the line corresponds to the diameter of the projectile. The color corresponds to the density, and all of the projectiles were traveling at 45 degrees, again, that average impact angle. But we see that they kind of only slow down at about 20 kilometers altitude, and they really only lose mass below 30 to 40 kilometers altitude. So again, this checks out with that Mars isn't affecting these projectiles very much before they hit the surface. However, if we look at Earth, we can see that it is affecting these projectiles. We have smaller projectiles that are being affected at a higher altitude on Earth than on Mars, and they are losing mass and slowing down within the correct realm of what we think is happening, or what we see is happening here on Earth, mostly below that 50-kilometer altitude. But if we look at Venus, what do you think is going to happen? It's craziness. So it's affecting these projectiles at a much higher altitude. Pretty much at 100 kilometers, it's significantly slowing them down and ablating them. And if we look at the atmospheres between Venus and Mars, between Venus and Earth, where they're being affected is within the stratosphere. And so that's where there's a significantly high amount of density that's increasing. And so we can see that Venus is significantly affecting what can get through. But now we can actually try and look at the individual projectile characteristics that survive to hit the surface. So here we can see the frequency of impacts for Mars, Earth, and Venus in red, blue, and orange for the density, velocity, and angle of trajectory. And again, this checks out with our current understanding of meteor physics, in that denser objects are more likely to get through on these different planets. The velocity is going to be averaging about that 17 kilometers per second because the higher velocity objects are moving so fast that they're building up more pressure and temperature and heat at their front. So they're blading and slowing down faster than some of the slower ones. But if you slow down velocity enough, it's actually moving too slow that it just kind of peters out and doesn't form a crater. Now, the initial angle of trajectory also matches what we see, where the objects that are coming in with a relatively short distance at that 90 degrees, just straight down to the surface, survive, where the ones at lower angles, closer to that 15 degrees, have more atmosphere to go through, and so they're being affected more significantly before they hit the surface. But the interesting thing to see is that we have density, velocity, and angle, but the diameter is significantly different across these different planets. So you can see here that the impactor diameter, the initial diameter of the impactors themselves, is different across these three planets. So Mars is letting in nearly all diameters from 1 meter all the way up to 10 kilometers. Earth's atmosphere is filtering things about 150 meters, starting to really filter those and get down, and then mostly can let in some of the smaller stuff though. Whereas Venus starts ablating and changing things at about 25 or 2,500 kilometers in diameter, and it's a pretty steep decline down to about 65 meters in diameter. So Earth has this nice kind of slope, but Venus has a very steep decline in what diameters it can actually let through. Now, if we look at the mass of projectiles that can actually hit the surface, this is a selection of projectiles at 20 kilometers per second at 45 degrees. And we can see that, so Mars is these circles, and Earth is the X's, and Venus is little stars, with the color of the point relating to the density of the object. So Mars is allowing all these different types of masses and is only kind of letting fewer ones in towards these really, really low masses. Whereas Earth is kind of falling off at a higher mass, but can still make these small craters. But Venus is slowing them down at a much higher mass and can't form craters below a couple of hundred meters in diameter. So if we take this back to our terrestrial craters that we looked at earlier, we can see that the Chixculub meteor would create a crater on Venus and Mars, about 100 meters on Venus and about a little bit bigger on Mars because Venus is affecting it more. If we look at meteor crater, it doesn't get through to form a crater on Venus, but it does form a larger crater on Mars. Tunguska does form a crater on Earth, but could burst at an altitude. But on Mars, it creates a crater more than like 1.5 kilometers in diameter. So it most likely doesn't burst at that altitude. And if we look at Chelyabinsk, it only makes a crater on Mars. It doesn't get through Earth or Venus. So with these, we can see that these three different planets are limiting the masses that can get through, no matter the velocity or angle. It's significantly affecting what can actually get through. So some of the applications for this is that we can take a lunar population of impactors and throw them through these three different planets and see what the expected crater population from the lunar distribution would look like on these different planets to try and get constraint on the age of these surfaces. Try and see when we get a distribution similar to what we see today. We can also try and look at different atmospheric conditions. We can try to evolve the atmosphere over time and see how that affects the crater populations. We also want to be able to build in different methodologies for fragmentation to be able to test the creation of these strewn fields on Earth, or these very unique crater clusters that we saw on Venus, which were about that 1.5 kilometer in diameter. And these, we don't really know what forms them or at what altitude they break up. So we can be able to see more of that with these models. We can also be able to use this in conjunction with current crater models to be able to get better constraints on the size of the crater. Right now, we have a relatively simple calculation for getting the diameter and depth with a constant density between three different planets. But if we took complexities in the substrate, we can get more accurate crater diameters. So, takeaways. Okay, there was a lot of talking, but we made a model. We made the atmospheric effects model, and it's a user-friendly modular code that people can use to test a lot of different theories in projectile characteristics and atmospheric effects on any different atmosphere. As long as you have temperature, pressure, and density, you can model it, and you can form any type of projectile population as long as it's spherical. We don't have other shapes built in yet, and be able to throw those through. So it's very modular. And people can use it for a lot of different tests. We can use the sensitivity of these models to get our analytical error. We found that mechanical models are more sensitive to differences in the velocity and mass equations than they are for the angle and lift coefficients. So things that are more affecting them, it's more sensitive. Things that aren't as affected, it's not as sensitive. It kind of checks out with what we have. Then the Venusian impactor population, this reinforces that the population of impactors that can actually get through to the surface is skewed towards these larger, denser objects. And so that's going to affect how we try and take a population from the moon, the flux of material that would have hit it, and thrown it to Venus. So we're trying to constrain the age of the surface here. But we're able to determine some of the mass limitations for Venus, Earth, and Mars to form a crater greater than 1 kilometer is about 10 to 7 kilograms for Mars, so relatively small. 10 to the 8th kilograms for Venus, that's a little less than, it's like 15 meters, 20 meters in diameter. But Venus is significantly larger, 10 to 10 kilograms. And so hopefully we've been able to convince you that we have this really awesome model and it works for Earth and we can use it for a lot of different planets. And this is only the beginning and we have so much more that we can do. It's going to be really exciting. So with that, I just want to thank my committee, Ryan Mills, Tamara Belsky, and Shane McGarry for helping me with this project. Again, I started this quite a few years ago, so it's good to bring it to a nice close and we actually get a paper out of it. I want to thank my mentors, Callan Bentley, Jennifer Witten, and Yannick Nedmasu, as well as my friends and family, my parents, Brenda and Robert, my fiance, Hunter, and all of my friends in the area, as well as the entire UNC Eames community for being so wonderful during this time of COVID and uncertainty, and being able to keep this community supporting its grad students. So, thank you. We can open it up to questions.
Yeah. Marissa, could you go back to the graph with all the Venus curves on it again?
The Venus curves. Let's see here.
Oh, so it's not an optical illusion. There's an inflection on the curves.
Yes.
And what's causing that? Why do they go vertical? It's like they go.
Yes, so that is on the mass remaining. We have these kind of distributions of things traveling at 10, 20, and 30 kilometers per second, where they're losing a lot of mass. And those projectiles, it's actually stopping. The velocity is reaching 0. So on the mass, it shows it as reaching a critical mass and then falling to the surface. So it kind of reaches an end point.
So if Mars did have an ocean back in time, had an atmosphere that was more Earth-like, or certainly had more water vapor, denser, is there enough sensitivity here? Do you see differences in the distribution of crater size with time?
That is a really good question, and I didn't look at it here just yet, but hopefully if we can be able to get the lunar population, we can actually throw it through the Martian atmosphere and be able to see what it would look like. And it's really interesting because there's actually theories that significantly large impacts actually depleted the Martian atmosphere. So kind of seeing how that might affect it as well could be an interesting avenue to go when trying to think about the ocean and the environment.
Hey, that was a really good talk. My question was about the underlying 3 equations that you had showed very early on in your presentation. And you showed that there were multiple equations that could explain each of those parameters. And maybe I missed it, but could you explain, like, did you use the same equations for each of those for all of these different planets that you looked at, or did those vary per planet?
Sure. Let me show you. Down here. So as an example for the variations in the velocity equation, we had all of these different equations that we could choose from, and we chose the ones from the 1971 Baldwin and Schaefer paper, which is one of the kind of first looks at this. It's very comprehensive in how they're building their model, and so we used those same equations across all 3 different planets, but you can use, the model has any of these that you can throw in there to be able to see what happens.
So my follow-up to that would be, why would I not use, or why would I want to use any of these other equations that you have in your model?
Sure. So they are all accurate to different models that we have and different methodologies and thinking of how these different parameters relate to one another. And so it's kind of a preference of what you're trying to model, i.e. like micrometeorites versus these larger meteorites. Because if you have something that's so big, you have a projectile population that's basically not going to ablate and not going to break up, then you don't really care so much about these different nuances. So if you want more nuance in your equation, you can use some of these different methodologies.
Yes.
Questions? Sounds good.
I don't know how to say.
If any attendees have questions, oh, I see one. Just raise your hand virtually and we'll unmute you. Alex Longo has a question.
Yeah, I'm just kind of wondering whether this model would be applicable to Titan, because Titan also has a thick atmosphere, but there's a lot of methane in there as well, and also your primary impactor population would probably be comets. Would this, so would you be able to apply this, these equations to Titan, or might you need something new? Thanks.
Yeah, thank you. No, that's a great question. And there have been recent models that have used hydrocodes to try and get the difference in Titan's atmospheric effects. And so you can use these to try and look at Titan's atmosphere as long as you have the pressure and density and pressure, but those chemical effects currently aren't built in to the model, so that would need to be expanded upon. But yeah, your impactor population would probably be different because you would have more outer solar system kind of Kuiper belt objects, so more cometary objects too, as well, that could be hitting that one. But you could definitely use this to try and look at that atmosphere.
Thank you.
It's
Can I ask a curiosity question? So these are largely drag equations, just variance on it. What are the equations that control the ablation rate? Like what physics sets the ablation of these things? I've
Yeah.
never seen them.
yeah. There. So we got some of the change in mass here. So we have a lot of the heat transfer coefficient and the heat of ablation. So it's how much of the heat is being transferred from the atmospheric molecules into the meteoroid. So we have a lot of that. It's also dependent on the density of the atmosphere, the area of the object itself, and the velocity that it's traveling at. But it's going to be mostly how much that heat.
Mostly frictional heating, is just blowing particles up.
Yeah, yeah, spalling and making it vaporized.
I have, I guess, a non-sciencey question, but which result surprised you the most?
Which result surprised me the most? So this is a fun slide that I didn't get to come into, but this is what we were looking at with the initial angle, mass, and velocity that can get to the surface to reach it. And what we had is that none of the projectiles were actually pancaking for Venus, which is really interesting. That actually hit the surface. Anything that exploded didn't form a crater. And so kind of going into more of that pancake factor and the altitude at which it would have burst would be really interesting to see here. And we currently have a limit of 10-kilometer diameter of what's going to ablate and break up. So that value may need to be scaled. It could be maybe overestimating the diameter. But if we have this for Earth, we get a similar kind of distribution where the mass is falling off and the pancake factors are increasing with the smaller craters being formed by more dispersed projectiles. But on Mars, we have kind of what we see, but then there's this weird pancake gap where the pancake factor that's exceeding, there's kind of this hole there. I'm not quite sure why it's there, but that could also be because we have a 100-meter diameter for the projectiles that are ablate or break up. And so that may need to be scaled up to maybe a larger diameter. So for Mars, it could be that these larger craters are formed from more dispersed fragments than what we currently think the 100-meter threshold is.
Thank you, and that was a great presentation.
We have another question from Alexis Lopez.
Hi, great job, Marissa. It was wonderful. But I was wondering if you've looked at experiments impact or experiments in the lab and compared the two, or anything like that, if that makes sense.
Yeah, so a lot of the equations that we have for these different changes in velocity and mass and fragmentation are from experimental observations in the lab, as well as observations in the field. And so the calculations themselves are kind of connected to those experimental observations as well. And that's a lot of work that happened in the 70s and 80s when these equations were being developed.
Okay, thank you.
Sorry, just as a follow-up, would you mind telling us what an experiment of making a crater looks like in a lab?
Oh my God, it's great. So they have like a pit of sand, and they can put sand and like different types of sediment underneath it. And then they basically take a big shooter and put it at a certain angle and have a certain velocity and a certain object, and then they go and they can see what kind of crater it makes. They can see the ejecta that gets deposited. But then the issue with that is we don't get a lot of the like vaporization and the real fragmentation of the pieces. But it's, yeah, they just shoot things into sand. Yeah.
I don't want to dominate the con. Does it matter that the surface temperature of Venus is, many hundreds of degrees and the rheology of the target materials is different?
Mm-hmm. Yeah, certainly. So the temperature and the density, so let's see, on Venus, it's about 900. It's very, very, very hot. But the pressure at the surface is about 92 times what we have here on Earth. And so that can really affect the rocks and how they're degrading over time too. So that can affect the crater population that we see. But yeah, the rheology is mostly basaltic lava flows in the plains, and then some granodiorite in more of the highly deformed mountainous areas. And right now we're assuming kind of just granite for everything, Earth, Mars, Venus. And so changing that up can change some of these results, but yeah.
Yeah.
Yeah, awesome. Well, thank you so much, guys. I hope you enjoyed it.